In this lesson, we will first introduce the simple linear regression model and the correlation coefficient. Inferences for the simple linear regression model will be discussed, and the important distinction between inference for mean response and inference for outcome will be clarified. Upon successful completion of this lesson, you will be able to 1. Use plots and summary statistics to describe the relationship between the response variable and the predictor variable. 2. Find the regression equation and interpret the results. And 3. Use the regression model and know the limitations. We just learned about chi-square analyses that test for variable independence. But what about the relationships that can exist between continuous variables? If we want to provide a measure of the strength of the relationship between two quantitative variables, a good way is to report the correlation coefficient between them. A correlation is defined as the quantification of the degree to which two random variables are related, provided the relationship is linear. The direction and magnitude of the linear correlation can be quantified with a correlation coefficient, which is abbreviated by r. The value of r can range from -1.0 to 1.0, with a value of 0 representing a situation where the two variables do not vary together at all. If the correlation coefficient is positive, the two variables tend to increase or decrease together, while if the correlation coefficient is negative, the two variables are inversely related. That is, as one variable increases, the other variable decreases. If the correlation coefficient is 1.0 or -1.0, the two variables vary together completely. That is, the graph of the data points forms a straight line. Suppose that we are interested in a pair of continuous random variables, each of which is measured on the same set of persons, countries, or other units of study. For example, we might wish to investigate the relationship between the percentage of children who have been immunized against the infectious diseases diphtheria, pertussis, and tetanus, also known as DPT, in a given country and the corresponding mortality rate for children under 5 years of age in that country. The United Nations Children's Fund considers the under 5 mortality rate to be one of the most important indicators of the level of well-being for a population of children. The data for a random sample of 20 countries are shown here, where we have the 20 different nations here, the percentage of children immunized, and the mortality rate per 1,000 live births here. If X represents the percentage of children immunized by age 1 year, and Y represents the under 5 mortality rate, we have a pair of outcomes, X sub I, Y sub I, for each nation in the sample, as shown here. The first country on the list, Bolivia, has a DPT immunization percentage of 77% and an under 5 mortality rate of 118 out of 1,000 live births. Therefore, the nation is represented by the data point 77, 118. Before we conduct any type of analysis, we should always create a two-way scatter plot of the data. If we place the outcomes of the X variable along the horizontal axis and the outcomes of the Y variable along the vertical axis, each point on the graph represents a combination of values, or X sub I, Y sub I. Remember scatter plots? Remember, it is an easy command line in RStudio, plot X, Y, and you can add complexity to the plot by defining the X and Y axis labels. Here is some command code for setting up a plot. If I read in my data that I called DPT data and have these two vectors within that data, I can plot it by doing this. I can make it more complex by adding labels, such as the label of the x-axis as percentage immunized against DPT and the y label as under 5 mortality rate per 1,000 live births. And this is what my plot will look like. Notice that the labels for the x and y axes are exactly as I wrote in my code to generate my scatter plot. We can often determine whether a relationship exists between x and y, the outcomes of the random variables x and y, simply by examining the graph. As an example, the data are plotted here with percentage of children immunized against DPT appearing on the horizontal or x-axis and the under 5 mortality rate on the vertical or y-axis. Not surprisingly, the mortality rate tends to decrease as the percentage of children immunized increases. But remember, we are really bad at interpreting data without biases involved, which is why we have inferential statistics tests that we can use to better and more appropriately analyze the data. If we want to provide a measure of the strength of the relationship between these two quantitative variables, a good way is to report the correlation coefficient between them. This is also called Pearson's coefficient of correlation and can be computed as little r as shown here, where you take into account the individual values minus their means, the sum of all of those multiplied together, and then take into account the sum of the squares of those differences and the square root of each of those times one another. Note, the sign of r indicates whether the two variables are positively or negatively correlated. As we will see later in the lecture, if we fit the simple linear regression model between y and x, then little r has the same sign as beta 1, which is the slope of the regression line and is always the quantity of interest. We'll come back to that when we talk about linear regression toward the end of this session. The correlation is also unit-free. We can see this easier using the equation above. Consider, for example, we are interested in the correlation between x equals height in inches and y equals weight in pounds. In the equation here, the numerator would have the units pounds underscore inches. The denominator would include taking the square root of pounds squared and inches squared, leaving us again with units of pounds underscore inches. It would look like this, where if you substitute if x is in pounds and y is in inches, these would be your unit distributions, and how you calculate it out, you would end up taking the square root of the square here, which would give you the same pounds underscore inches, which eventually will cancel each other out. So the units would cancel out. Also notice that the correlation value would be the same regardless of which variable we defined as x and y. The remarks or reminders that are listed here in blue at the bottom of the slide tell us that r takes the value between -1 and 1 inclusively. As the magnitude of r approaches 1, the stronger the linear relationship is. The sign of the correlation provides direction of the linear relationship, meaning whether it's positive or negative. As the magnitude of r, little r, approaches 0, the weaker the linear relationship is. And, as a reminder, there are no units attached to little r, as they're canceled out by the given equation as worked out at the top of the slide. As a recap, correlations can suggest relationships between sets of data. The correlation coefficient, also known as little r, provides a measure of how related two variables are, and it is expressed as a value between +1 and -1. The closer the value is to 0, the weaker the correlation. So the null hypothesis would be that there is no correlation, and it would look like this here. For any given question about correlation, if you're calculating the correlation coefficient, your null hypothesis can look like this, where little r is equal to 0, which would give you an alternative hypothesis of little r is not equal to 0. Hopefully you remember this is a two-tailed test. And hopefully you remember that, or can think about it, that you have a plus or minus situation with +1 or -1 as far as the correlation coefficient, as the number will always reside between -1 and +1. And this should tell you automatically that you're dealing with a two-tailed test. So for example, if you plot the width of an oak tree leaf, y, on the xy scatter plot as a function of the leaf's length, or x, the correlation coefficient, or little r, indicates how much width depends on length. An r value equal to +1 would indicate a perfect positive correlation between width and length. In other words, the longer an oak leaf, the wider it is. An r value of -1 would indicate a perfect negative correlation, i.e., the longer an oak leaf, the narrower it is. If there is no correlation between two variables, the r value equals 0, which would mean that there is no relationship between oak leaf length and width. The null hypothesis for a correlation is that there is no correlation and r equals 0, as shown here. Let's look at another example. Students wanted to see if there's an association between the mass of tomatoes on a tomato plant and the number of seeds in the tomatoes. They picked 10 tomatoes from the plant, cut each one open, and counted the seeds within. The data are listed here on the left in the table shown. The null hypothesis here is, as written here, r equals 0. The alternative hypothesis is that r does not equal 0. Again, a two-tailed test of correlation. The calculated r is shown here, where I have worked out the equation for r, which is shown here. What I did in Excel, because I used Excel for this, is I just worked out each one of these factors, so x sub I minus the mean. So x minus the mean is what this value is here, so 77.5 minus 78.03 gives you a negative 0.53. The same thing for the y variable, so yi is this one here, 20 minus the mean, which is 22, so negative 2. Then for each one of these, to get the value of the sum of these individual differences, so these here and these here, to get this value here, or this one here, is you take x, which is this here, and y, which are these here, x times y, so this times that equals 1.06. You do this all for all 10 tomato plants, and then you sum that up, and this value here goes here. Then for these values here, you take this value and square it, and you take this value and square it, and then you add those all together and get the sums, and that's what goes in these positions. You take the square root of those, multiply them together, and you get this value. You divide 67.6 by 74.78, and you get 0.904. That is your correlation coefficient value. Now, the degrees of freedom for a correlation coefficient are defined by the number of pairs of observations, because these are paired observations. Both of these values represent the tomato plant number 1, or tomato number 1, and total number of pairs minus 2, so you had 10 total tomatoes, minus 2 equals 8, so your degrees of freedom are 8. This is important because in order to know whether or not we can consider this R value significant, is we need to, of course, consult our table. The table that we're going to be consulting for the Pearson's correlation coefficient is called the critical values table for Pearson's little r. We are interested in a p equals 0.05. As it wasn't, I didn't tell you what it was, so you always assume it's 0.05. Again, this is a two-tailed test, and we had 8 degrees of freedom, so our critical value is 0.632. So the value for R crit is plus or minus 0.632 for 8 degrees of freedom. Again, 10 pairs of observations minus 2. The calculated R value was 0.904, which is much closer to positive 1, a perfect positive correlation, than to 0.632. This means that the probability of getting a value as extreme as 0.904 purely by chance, if the null hypothesis is true, or little r equals 0, is less than 0.05. Therefore, students can reject the null hypothesis and conclude that there is a statistically significant association between the mass of the student's tomatoes and the number of seeds each tomato has. To go a step further, it is possible to calculate the coefficient of determination, which is called R squared. Really simple, you take the R value, which was 0.904, square it, and you get this coefficient of determination, which is 0.817. This value, or the R squared value, denotes the strength of the linear association between the mass of tomatoes, or X, and the number of seeds, Y. The closer the number is to 1, the stronger the association. Also, R squared tells us the fraction of variance shared between the two variables. Finally, a scatter plot graph can be used to illustrate the relationship. It is possible to draw a straight line that goes through the points called a line of best fit. Here is the RStudio command code to generate a scatter plot with a best fit line. I have read in the data on the tomato seeds that on my computer was called tom-seeds.csv. I named the data set Tom Data. I ran the easy plot command, so plot parentheses your X value, your Y value, and then I labeled those. So tomato plant mass is your X label, number of tomato seeds is your Y label. And then I added this best fit line with the command code AB line, parentheses LM, which stands for linear model. We're going to come back to that a little bit later in the session. And then again, you tell it your data sets, but this time they're in reverse order because you're looking at the linear model. This line tells us that Y is related to the interaction between X and Y, which is why you put Y first here. You'll understand that better as we talk about linear regression in a little bit. And again, I colored it red here. So the line of best fit may pass through some of the points as shown here, like really only this one here, or all of the points. Statistics are correlation coefficient, the little r, and the coefficient of determination, little r squared, shown up here. So these are our statistic values. So our p-value automatically tells you there's a significant relationship. The R square value, again, is the correlation of determination, and the R value is the correlation coefficient. The coefficient of determination is a measure of how well the regression line represents the data. If the regression line passes exactly through every point on the scatter plot, it would be able to explain all of the variation within your data. The further the line is away from the points, the less it is able to explain that variation. In the scatter plot and best fit line figure shown here, 81.7% of the variation in Y can be explained by the relationship between X and Y. This means that 81.7% of the variability in tomato seed numbers is associated with the variability in the tomato plant mass. We get that value from our R squared because this describes this best fit line. 81.7% of the variation in the Y variable is described by the interaction between X and Y. Many biological traits, especially animal behavior or physical appearance, vary greatly among individuals in a population. Thus, a coefficient of determination of 0.817 between two biological variables is considered quite high. Now we will look at the simple linear regression model to understand the linear equation explaining the correlation coefficient. In other words, what does the best fit line tell us about the data? Regression analysis is a tool to investigate how two or more variables are related. Quite often, we want to see how a certain variable of interest is affected by one or more variables. One may want to use a person's height, gender, race, etc. to predict the person's weight. Let us first consider the simplest case, using a person's height to predict the person's weight. Let's look at how we might set this up. You can have a variable of interest, denoted as y, which is equal to weight in this example. It is also called the response variable or dependent variable. Then you have the predictor variable, which we denote as x. This is height in this example. It is also called the explanatory variable or independent variable. When there is only one predictor variable, we refer to the regression model as a simple linear regression model. Think about the following. If you are asked to estimate the weight of a student in this course, what would you use as a point estimate? Think about it for a minute. What would you need to know, or what would you use as your point estimate? The best case would be the mean weight of the class or the median weight of the class. That would be a good point estimate to start from. Now, if I tell you that the height of the student is 70 inches, can you give a better estimate of the person's weight? The answer is yes, if you have some idea about how height and weight are related. Okay, so now let's look at interpreting the coefficients of the linear equation. If we sample the heights and weights of students from UAB, we might obtain data that looks like this. First, we should use a scatter plot to represent the data. Again, using RStudio, this is easy. Just read in the data and use the plot command as done before. Like this. Remember, you can name the labels and title of the graph to make it clear what your scatter plot is representing. The relationship plotted here looks linear. We can thus fit a straight line to the data using the least squares method, the smallest possible sum of squared error. Here is what this model would look like. The model is, I'm going to put this back up here. So the model tells us that y equals beta sub 0 plus beta sub 1 times x plus epsilon, where beta sub 0 and beta 1 are unknown values, and epsilon is the random error with a mean of 0. So the model for this example would look like this, where y equals weight, or WT for short, and x is height, or HT for short. You might recognize the equation here as the equation that we use to define a straight line. Y equals mx plus b, where m equals the slope of the line and b represents the y-intercept. Remember that? So in this case, this would be your b value or your y-intercept value. Beta sub 1 is your m value. And remember, this is equal to 0. We can estimate the value of y, or weight, by using the point on the regression line corresponding to the value of height equals 70 inches. Remember, we want to find a model that will help us predict the weight of a student who is 70 inches tall. We are going to solve this statistic using RStudio. Here's the command we use to run a simple linear regression, also called a linear model, which equals LM. I told you we would come back to that in a minute. Remember when we plotted the data before, the data set before, we can add, so this is showing you the scatter plot for the height and weight data from UAB. And what we've done is we've added a linear model line, so the same command line, ab line, parentheses LM for linear model, parentheses our data sets, Again, the y is being described by the xy interaction, and we've colored it red. What we've done in RStudio is we've added a line to describe what our model is. Our model equals linear model, LM, and here we have our data set just as we wrote it here. Okay, so it's just asking to set up our model that has predicted this red line. And then we write summary as we want to summarize the model. And this is what the output of that looks like. So we've told RStudio that our model equals linear model with our two data points, y to x, and this explains to RStudio how to associate the fit line to the data points based on how y can be explained by the relationship between x and y. We also have to call for a summary of the model itself so that we can see the output, which is shown here. To get the regression line equation, you look here, which is called the coefficients table. The y-intercept is, as shown here in parentheses, the intercept is this estimated value here, which is negative 222.479. And the slope, or m, of your y equals mxb equation is 5.488, which is shown here. Also in this table are the standard error here. The t-values, or t-statistics, we'll come back to this, and the p-values, and we'll come back to those a little bit later in the section. So first, let's look at what our equation looks like. Our equation for the best fit regression line, which is depicted by the red line on our scatter plot here, can be written as weight equals 5.488 times height minus 222.479, as shown here. So to answer the question of what weight a student with height of 70 inches, we can use the equation to calculate an estimated weight. We substitute the value 70 where our height variable is, multiply this out, subtract our y-intercept, and we can predict an estimated weight of a student that is 70 inches tall would be 161.8 pounds based on our least squared models that fit the regression line for the data points we put in. The coefficients of determination for this example were also calculated using the model. So let's look back at our model output here. Remember the coefficient of determination? We also call it the R-square value. The coefficient of determination measures the percentage of variability within the y values that can be explained by the regression model. Thus, a value close to 100% means that the model is very useful, and a value close to 0 means that the model is not useful. In our example here, the R-square value is 0.506, which is right here, multiple R squared, 0.5057. We'll round it up to 0.506. This can also be expressed as a percentage. So the R squared value could also be expressed as 50.6%. And if we think about understanding the regression equation, the constant term, or the b, okay, so in y equals mx plus b, is the y-intercept of the regression line. When x is equal to 0, when x, the value, is within the scope of observation, then that value is the estimated value of y when x is 0. However, when x equals 0 is not within the scope of the observation, the y-intercept is usually not of interest. In our example, x equals 0 is not clearly within the scope of the observation since no one has height of 0. The value beta sub naught, or b, within that y equals mx plus b equation, or the y-intercept, by itself is not of much interest other than being the constant term for the regression line. The coefficient of x, or beta sub 1, or m in the y equals mx plus b equation, is the slope of the regression line and is always a quantity of interest. This value represents the estimated increase in y per unit increase in x. Note that the increase may be negative, which is reflected when this value, beta sub 1, is negative. There are cautions with looking or understanding linear regressions. First, extrapolation should be used with caution. Extrapolation is applying a regression model to x values outside the range of sample x values to predict values of the response variable y. For example, you would not want to use your age in months to predict your weight using a regression model that used the age of infants in month to predict their weight, because the growth patterns would not describe each other the same. Second, the fact that there is no linear relationship, in other words, the correlation is 0, does not imply there is no relationship altogether between the x and the y. Use scatter plot to explore whether other possible relationships may exist. These 4 graphs illustrate 4 possible situations for the values of r. Pay particular attention to the graph D, which shows an example where x and y are related, but not linearly related. In other words, the correlation is 0, but it's obvious to see that the values between the x variables and the y variables are highly related. It's just not in a linear fashion. First, let's do a quick review of what we've already gone over related to correlation that also relate to what we're learning about linear regression. If we want to provide a measure of the strength of the relationship between 2 quantitative variables, a good way is to report the correlation coefficient between them. From the sample, we can compute the sample correlation coefficient using the formula like we did previously. Remember, r always takes a value between -1 and +1. If the magnitude of r is close to 1, the linear relationship is strong. If r is close to 0, it indicates no linear relationship. The sign of r indicates whether the 2 variables are positively or negatively correlated. If we fit the simple linear regression model between x and y, then little r has the same sign as beta sub 1, which is the coefficient of x in the linear regression equation as we were just talking about, the slope of the line. Instead of working out the formula for the example, for this example we're talking about, let's use RStudio instead. We can use a new command function, which is a correlation test, which is the command code core.test or correlation test. And this will conduct a Pearson's correlation test. Here's the output, which shows a correlation coefficient, or R value, equal to 0.711, with a p-value of 2.218 times 10 to the -5th. This is very low. The 95% confidence interval is also calculated and is defined here by this model as between 0.46 and 0.85. This indicates a significant result in a fairly strong relationship between height and weight, as the correlation R equals 0.711, which is close to 1. Now let's talk about making inferences about these correlation coefficients. The Pearson correlation is the sample correlation coefficient, or R. The p-value is for testing about the population correlation coefficient, or little p. You can set the hypotheses up to be that little p is equal to 0, where x and y are linearly independent, where the alternative hypothesis is little p is not equal to 0, where x and y are linearly dependent. For the height and weight data, if we look at the output, we can see that for the variable height, the p-value is equal to 0, or close to 0. Therefore, for any reasonable alpha level, we can reject the hypothesis that the population correlation coefficient is 0 and conclude that they are non-zero. In other words, that x and y are linearly dependent. In addition, we can make inferences about the slope of the population. In other words, we can test whether x, or height, is a statistically significant predictor of y, or weight. Since beta sub 1, the slope of the population regression model, indicates the relationship between x and y, we often want to make inferences about that slope. For example, we can set up our hypotheses about this to look like this. So similar as we've already talked about, our slope, or beta sub 1, is equal to 0. The alternative hypothesis is that the slope, or beta sub 1, is not equal to 0. The slope test is testing whether x is a statistically significant linear predictor of y. The test statistic looks like this. Alternatively, to test whether beta sub 1 is greater than 0, we are testing whether x is a statistically significant positive linear predictor of y. To test whether beta sub 1 is less than 0, we are testing whether x is a statistically significant negative linear predictor of y. RStudio's output for the linear model gives the result for two tailed tests for beta sub 0 and beta sub 1. Remember, for the data and height and weight example, the regression model looks like this, where you have weight is equal to beta sub 0 plus beta sub 1 times height plus epsilon, which is equal to 0. We can test whether height is a statistically significant linear predictor of weight by testing the hypothesis as shown here. And if we look again at the output for our linear model, we see that the t-value for the test statistic for the coefficient, remember as given here, is 5.16, and that the p-value is less than 0.001. Since the p-value is very small, we can reject the null hypothesis and conclude that height is a statistically significant linear predictor of weight for any reasonable alpha value. So throughout this section, we intermingled both the calculations for correlation coefficients and the linear model or linear regression calculations to understand relationships and how we identify and infer information about relationships between two quantitative variables. After this lesson, you might be asking yourself, what is the difference between a correlation and a regression? From a correlation, we can only get an index that describes the linear relationship between two random variables. On the other hand, from a regression, we can predict or estimate the value of a response that is associated with a fixed value of the explanatory variable. Simply, a regression explores the nature of the relationship between two continuous random variables. Correlation computes the value of the Pearson correlation coefficient, also known as little r. Its values range from -1 to +1. A linear regression quantifies the goodness of fit with r squared to the best fit linear line for the data. I hope this clears it up and you all understand how correlation and linear regression are different, but also how they help you describe the interactions between the data together.